All right, let's continue. Jashank's just set up a couple of things for you to do, in particular the lab for installing your Postgres server. Why is that so slow? Did I not click? I did click on it. One trick with WebCMS 2, this little box here that you get when you click on one of those things is really just what? WebCMS 3. The thing you get here is really just a preview box. So you're probably better off clicking on that thing there, so it opens up a whole window version, so probably easy to read there. So that will tell you what to do. It steps you. Look, it's gigantic. It gives you so much help, and there's even the experts El Cheapo version, quick summary, so if you can't be bothered reading the rest and you're able to fix all the problems that you create all by yourself, then you can just use that. Otherwise, step by step through all of this stuff. Alright, so let's get back here. Okay, so relational databases, what do? They obviously allow you to store and modify data, but they also allow you to store and modify metadata, which is stored in a database as data, which is a nice cute circularity. So the metadata is the stuff in the catalogue which tells you that you've got a table and it's got these columns and blah blah blah. So the stuff that appears when you do a \d in Postgres. Also, specifying constraints, extremely important aspect of databases, to make sure that your data is consistent and has sufficient integrity. Allow you to manipulate data declaratively using SQL. Allow you to extend the capabilities of the database using views, so you can have virtual tables if you like. Triggers. How many people have played with triggers? One, two. No, not necessarily. They might not have been in 9311. Right. In what database? Yeah.
SQL Server.
Right. Okay. So Postgres triggers look different, and stored procedures as well. Postgres provides a way of rewriting queries before they're executed, and in fact that's the way Postgres implements views, by specifying a rule. So it says, defines a, you create a view. What it actually gives you is a rule that says, if the user asks to look at this table, then actually do this query to get the data. Indexes, of course, for optimizing transaction processing. Postgres was possibly the first database to use multi-version concurrency control, which I see that databases like Oracle and so on have now adopted. So all databases, regardless of the type, will use the relational model, and they'll have some flavour of SQL. SQL is supposed to be a standard, but annoyingly every database tweaks it a little bit, which I suspect is related to vendor lock-in or something like that. So if I do things like this in Postgres, what it actually does, it adds stuff to the catalogue. So it updates data, but it doesn't update the regular data, it updates the metadata. So doing create table statement like this will add tuples to a whole bunch of tables that we can look at. In fact, maybe we can look at them right now. So if you open up Postgres, doesn't matter what database, Let's just use that one. I shouldn't have done that without practicing first. Aha. Right, so all of these tables are the Postgres catalogue. And so if you look in some of these tables, and I think PG class is the table that represents tables. So when you define a table, you get an entry in PG class. And of course, since these things are essentially tables, you can ask queries on them. And you get a whole lot of information like that. Probably not that helpful. I'll talk about toast in a minute, but you can see there's an entry for courses. So that's the entry for the courses table that tells various information about the courses table, like who was the user who created that table. Well, what else does it tell you? I think this R here is something that actually says this is a table. So Postgres was originally developed as an object-oriented type of database, and so hence the word class. And one type of class is a table. And there's all these other things are flags and so on, and there's probably information that talks about the storage structures in the table as well. But the normal way that you interact with this data is to use the meta commands with the appropriate thing. So this will tell you all the information about that table. So we've got that entry in the PG class table, and then there's going to be an entry in the PG attribute table for each of these with a foreign key referring to the class table. So we know that there are 4 attributes, and then there'll be another entries in the attribute table that refer to the type table. So there's all these different tables floating around in the catalogue that describe things like the table, where is it? Attribute definitions, attribute, databases. Inside each database there's a table telling you what all the databases are. All the operators are stored in a database. I'm trying to find type, where is it? Blah blah blah. PG type, and database users as well. This table, well, that's actually a view. And then there's my actual tables that I inserted. So, given that you've got all of these catalogue tables, you can actually ask queries on it. And in fact, if you think about it, when I do \d, that's just running a query on all of those tables to tell me what the particular tables stored in the system are. There's a way of getting Postgres, I think. Well, that just gives you more information. There's a way of getting it to print out the actual query that it's asking to produce that information. In any case. So there's all those catalogue tables that hold all of the metadata. So when you do a DDL statement, like create a table, you feed it into the DBMS and it makes changes to the catalogues. It might make some changes to the index if you say, right, in fact, if you create a primary key, Postgres always creates a B-tree index on that attribute. So potentially it can update the indexes as well. And it'll return a status, which simply tells you whether the table was created or not. Constraints, if I look more carefully in that catalogue, I think there's a PG_constraint table as well. So there's various kinds of constraints that you can have in a database. You can have constraints on attributes, which basically is talking about either the types or restrictions on the values that the attributes can have. So varchar 40 is that. And one thing that was probably obvious from looking at things like this, I always do that, try to run Postgres commands while I'm not actually logged into Postgres. I should. The types that you see here don't look necessarily like the ones that you fed in. So there's if you say, you know, char 8, it turns into character 8. If you say varchar, it turns into something else. And that's the internal data types that Postgres manipulates. And that's part of the first assignment is to, well, in fact, that first assignment is to get you to implement a new data type for Postgres. Right, so let's go back here. So various kinds of constraints. Another thing that you'll notice if you ever get a dump of a Postgres database, which is very easy to do, you can just go pg dump and give the name of the database, and it will give you all of the commands needed to rebuild that database. So you can take this file, port it somewhere else to another Postgres database, and then it will just load up. Now, some of these things are probably not portable to anything other than Postgres, but most of the stuff is portable and SQL standard, unlike SQL Server, MySQL, Access, SQLite, who all, when you do a dump, gives you something in a format that's definitely not SQL standard. But Postgres is pretty good from that perspective, so you can recognise that the one thing that's non-standard is the copy statement, which allows you to load up tuples in a compact way. The other way, of course, and I'm pretty sure you can actually force the dump to include that, is to have insert statements for all of the tuples. Similarly, when you insert tuples into tables, that's obviously going to add some entries to one of the tables in the database, and will probably make a few little changes to other fields in the catalogue, because one of the things the catalogue stores, it actually stores a count of the number of tuples in each table. So if you're adding or deleting, then obviously that's going to affect that count. And similarly, if you've got an index on a table, when you insert a new tuple, it's obviously going to update the index to take account of the values in that tuple. So that's how a statement like insert or delete is going to affect the stuff stored on disk. So the most common thing that we do with databases, however, is that we feed in an SQL query and we get back a bunch of results. That doesn't necessarily affect the data stored on disk. Maybe there's some logging stuff that gets updated, but basically what goes in, a piece of text representing an SQL query. If it's a valid piece of SQL, then it will execute it and you'll get back a result table displayed in text format. So what we want to do in this course is to look inside this box and look at what's actually stored on the disk. Why do we care about that? Well, potentially, if we have a vague understanding of what the query processor is doing, then maybe we can do a better job of writing queries. So we can write queries that are more efficient. And of course, the educational reason why we're interested is that DBMSs contain lots of interesting algorithms and data structures, and knowing about them is good because you might actually be able to use them outside the DBMS. So here's the inside of the box at a very high level. So our SQL query goes in as a piece of text, gets parsed, turned into a tree format relational algebra expression, which is then run through an optimizer, which basically does transformations on the relational algebra tree in such a way that it thinks those transformations are going to make the query execute efficiently. What you get at the end of that is a sequence of relational algebra operations, and not just I'm going to do a join, but I'm going to do a particular kind of join. So one thing about DBMSs is that they will often contain multiple multiple algorithms to implement a particular operation. So part of what the query optimizer is doing is looking at the query, looking at the structure of the query, looking at the data that's flowing in and out of the operation, looking at the constraints, is it a primary key, blah, 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 and working out which of the join operations is likely to be the most efficient. Postgres has an interesting query optimizer in that it uses a genetic algorithm. So it generates optimized trees and then applies a fitness function and says, aha, this thing that I've just generated looks better than that one there, so I'll keep looking at this one, then I'll transform that a little bit more. Does it look better? I'll continue down that path. So we can have a look at that later in the semester. So anyway, what we get at the end is a sequence of relational algebra operations to be executed by the database engine, which will produce a sequence of tuples which then gets displayed. So the DB engine is where we're going to be spending a lot of the time looking at how the relational algebra operations are actually implemented. And so that's a flow diagram, if you like, of what happens with a query, the structure of the database, and this really is basically reflecting the structure of the course. So we've got data stored on the disk in a particular format, and we're going to look at what that is. Then we've got something that manages that stored data, understands the formats, understands which file contains which set of tuples, for example. On top of that, once we've fetched some stuff from the disk, we want to potentially save it in a buffer pool, and in fact we definitely want to save it in a buffer pool because going to the disk all the time is a bad idea. Later on, so what the buffer manager does, it manages chunks of data, blocks of data. Then on top of that, we've got various file structures and access methods that tell us, all right, this is an indexed file, it's got a B tree, and I can use that B tree to find the appropriate tuples that I want. On top of that, we've got various relational algebra operators like join and so on, various implementations of them. And on top of that, we've got the query evaluator, which decides which of these relational algebra operators to use, which then invokes the appropriate access methods and so on, trickling down to the stored data. If you are writing a database to be a single-user database, you can just focus on that stack, and your code would probably not be super large. But as soon as you have to worry about concurrency and about recovery is extremely important because databases often contain mission-critical data, and you want to make sure if you have a system crash or whatever, you can recover the database to a sensible state. That code sort of infiltrates all of these parts of the system and makes them a lot more complicated than they would otherwise be. But in any case, we're going to basically work our way up from the bottom, looking at all of these components. So one very important factor that I'll probably keep coming back to over and over again, and I've already mentioned it once, was the difference or the issue of bulk data storage on large devices which are typically relatively slow, and manipulating data in memory. So ultimately, if we want to do anything to the data, we've got to get into memory and start fiddling with it there, whether it's extracting a few tuples from a block of data that's been read in from a table, or whether it's actually modifying the values that are stored in a block because we're doing an update or something. We have to get the data into memory. Memory's fast. Once we've got it into a memory buffer, it's fast to manipulate. Getting it into the buffer is very slow relative to the cost of manipulating it in memory. Now, in the past, this has always been phrased in terms of disks. So we've got spinning disks, and they have certain characteristics. In particular, they're quite slow compared to the speed of manipulating things in memory. Nowadays, a lot of machines don't have disks, like my laptop here, so it uses SSD storage, and that changes the properties a little bit, but SSD is still a lot slower than main memory. It's not, you know, order of magnitude like a disk is, but it's still, in fact, it is an order of magnitude slower than main memory, but a disk is even slower than that. But in any case, SSDs still aren't huge, even though, you know, there's 256 gigabytes of them in here. But, you know, if you want giant amounts of storage, it's all going to be on disks still. So, given that disks are very slow and we have to get stuff into memory to process it, once we've got it in, we may as well leave it hanging around just in case we need it again. And there are plenty of database algorithms where that definitely happens. So if you're doing something like a nested loop join, once you've got one page of data in, you want to keep that in memory because you're going to iterate through it one tuple at a time while you're dealing with other pages of data. So minimize the amount of data traffic between memory and disk. Also, of course, you don't want to have exorbitant storage structures where a tuple, which is varchar 200, always occupies 200 bytes. So if the string that you're storing is only 10 bytes long, you want the tuple to be about that size. So setting that aside, going a little bit more abstract again, a relational database engine, I would argue you could treat it as a relational algebra virtual machine. So all it does is execute relational algebra operations and tie them together. So here's the standard set of relational algebra operations, although sort, group and aggregate tend to be added on, but selection, projection and join definitely, and the set operations as well. So I've mentioned a couple of times, for a given relational algebra operation like selection, there's potentially a whole lot of different ways you could do it. From the completely stupid way of, look at the first tuple, does this satisfy my selection condition? Yes, good. Look at the next tuple, does this satisfy? Look at the next tuple, look at the next tuple, look at the next tuple. So a linear scan looking at all the tuples is not generally a good way to do things. Having an index, having a B tree, or hashing the data are generally going to be much better ways of doing things. But even with hashing, there's a whole lot of issues to take into account. If you're hashing on a single attribute, that's nice, but only certain kinds of queries are going to work effectively. Only queries that involve that attribute, and in fact only queries that involve equality operations on that attribute. So a cheap and nasty database might provide one or two ways of doing select, project and join, but something like Postgres or Oracle or SQL Server will typically have a lot of different approaches for implementing each of those operations, and that's what the query optimizer has to sort out. Let me see. Relational algebra is basically a way of manipulating relations. That kind of makes sense. So all array operators return a result, which is a relation, which is nice because that result can be fed into another relational algebra operator. And Jashank is looking mesmerised for some reason that I can't fathom. So any SQL query you ask, as I mentioned before, is going to be compiled, if you like, into a sequence of relational algebra operations. So here's an example, which is a query. It's probably a query from earlier on, but basically effectively doing a join on two tables and then doing a selection on tuples from, on attributes from the two different tables, and then projecting out the result. So there's a number of different ways that you could express that. So in this first example here, we do a select on relation R1, store an intermediate result, do a select on R2, store an intermediate result, then join those two temporary tables, and then to give a third temporary table, and then we do a projection on that. Now, this join doesn't necessarily require us to store that. Potentially, the stuff that's being generated from here, rather than being stored, could be fed into a join operator where we use a temporary table that we've created, but we're streaming the results of another selection into the join algorithm on that table. Another way, these are all ways of expressing the same thing. Now, anyone want to hazard a guess as to which would probably be the least efficient? The last one, because we're doing a straight join on the two tables and potentially producing a very large intermediate result, which we're then filtering down to the size that we want it. So here we're doing these two selections to produce smallish intermediate tables, then doing a join on two small tables. And as we'll see when we talk about join algorithms, if you've got very small tables, you can actually do joins very efficiently with a single pass across the second table in the join. So this is going to produce a large result which we then have to select over. And another thing about this is, because it's an intermediate result, we're not necessarily going to put an index on it. We might build an index as we do the join, but if we don't put an index on it, then this selection operation basically does have to do a linear scan, checking for tuples that satisfy the condition. So that's the kind of reasoning, if you like, that a query optimizer has to do to decide which. So in theory, it could choose any of these approaches to do to evaluate this query, but choosing that one would lead to very poor performance. Choosing that one's likely to lead to good performance. All right, let's have a look at that same query as we had before. All the students who pass COMP9315, but this time express it in a form like we just looked at. Ooh, that's not the one I wanted, that's the one. Right, so I've already seen the original query. So let's say it was s.z, comma. I think we might have done more than that, actually. We did the grade as well. And I won't write it out in full. Okay, so that's how we can do it. Something like that in SQL. What about in relational algebra? One possibility is to start out with courses. Select where the code is equal to 9315 and the term is equal to ANS2. If we do that, that's quite nice because how many tuples do we get? One. We get one tuple in that temporary table, which is quite useful. We could then do we could do a join on course ID, or in fact, I'm kind of just making this notation up as I go to some extent, but you get the idea, and yeah, thanks. So the number of tuples we're going to get there, well, just as many as students who are involved in the course. That's more than we need because maybe some people failed and they're not going to appear in the final result. So you might think, maybe we could do something. Ooh. Actually, I just thought of something. If temp 1 is just a single tuple, then potentially we could use that to do a select on the enrolments table rather than a join. I mean, that join's going to be very efficient because we've only got one tuple in temp 1. But all right, in any case, and then temp 3 is going to be another join.
Why don't we first select?
Sorry?
Why don't we first select people who actually passed before we do
Yeah, we could. Sure. So I was just doing a quick one and then I was going to say, hey, how can we do it better? Right, no, that's fine. That's good. So what are we doing here? We're joining that with students. Or maybe we can delay that until we've got exactly the students that we wanted, because at this point here we can select out the people who passed. Is that what you were suggesting? Yeah. Alright, so we could from temp 2 to do something like that, and then temp 3, that's obviously not going to be temp 3, that's going to be temp 4, and then we can join on students, so we can put together the student name and so on. And at the moment I think we've got all the enrolment data, and then that would give us the set of tuples we want, but each tuple would have too much information, so our final result would just be a projection of the fields that we actually wanted. So student ID, name and mark from temp 4. Okay, hopefully that's right. Anyone see a problem with that? Good. Okay, so when we were coming up with that, there was considerations of how can we make the intermediate results small, how can we generate the intermediate results more efficiently. Like I said, all this stuff will be sitting in the exercises directory after the lecture. Okay, defining the semantics of relational algebra operations. I don't think I'm actually going to bother with that because I think we all know. So we know that a selection is a set of tuples such that each tuple satisfies the condition that we're after. And projection is a set of tuples where a set of tuples where we have filtered out some of the attributes from each of the tuples. So we're producing new tuples from the original tuples. Technically, relational algebra should produce a set. Most DBMSs for something like this would produce a bag. So if projecting out a set of attributes produced two tuples with the same values, then just keep it. But and you can use distinct if you don't want that. Set operations, blah, blah, blah. You can read through all these. Hopefully you all know how all these operations work. Oh, actually, one thing, giving a little bit of a clue about how some of these operations might work, this is actually not a very good way of implementing this necessarily. This is nested loop join. So we read in a tuple from the outer relation, and then for each tuple in the inner relation we check whether the join condition is satisfied, and if it is, we stick it in the result set. Okay. Now, we can potentially make that slightly efficient if we read in a big chunk of tuples from R, and then we scan through the tuples of S. In fact, if there's only one chunk of tuples from S and only one chunk of tuples from R, we simply read those two blocks of data and then we can do everything in memory. So that's about as efficient as you can get. But depending on how much buffer space you've got to play around with, you can potentially make this behave like what I just described. You can read in one block of data from one relation, and then if you can fit the other relation in memory, then you can do the join check here, which is this matches test on each pair of tuples from those. Then you read in the next block of data from the other relation, next block of data, next block of data. So for both relations, you simply scan the data once, and that's as good as you can do with a join. If you have to do repeated scans of data, that's not so good. Definition of left outer join. Alright, so let's quickly, before we go, have a look at Postgres. So it's, as I said, DBMS is a relational engine. Postgres gives you all of the relational operators, potentially with very efficient implementation of those operators. Good transaction processing, so full ACID, good backup and recovery, and an interesting query optimizer that I alluded to before, and a whole bunch of different data types that you can manipulate. So JSON was added in one of the recent versions of Postgres as a built-in data type, and in one of the more recent versions of Postgres they also added replication, so that you can have more reliability, distribute the data. The replication part of Postgres is really still ongoing. Postgres comes with a bunch of non-standard data types, but it also, one of the really nice things that I thought about Postgres when I first came across it was the nice extensibility model, so it makes it relatively straightforward to add your own data types, which didn't seem to be the case with a lot of other databases. Maybe they've all improved, and Postgres is reasonably standards compliant. There's some of the people who are involved in developing it. So we've already seen that you interact using PSQL and you give a database name. There's the example of interaction through the PSQL library, through the PSQL application. Here's an example using PHP to grab data from the database using a query. Select star from calendar and then fetching each of the tuples and treating it as a PHP object. So it deals with lots of different kinds of data. Users, nowadays, I think they're called roles, and they've kind of bundled the notion of group and user into a single thing. The part of the catalogue schema is the list of databases, and some parts of the catalogue, it's interesting, some parts of the catalogue are localised to a particular database, some parts of the catalogue are global, and obviously something like the list of databases in the local Postgres instance is going to be shared across all of the databases. Notion of namespaces, tables, views, blah, 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 aggregates, easy to define your own aggregates, easy to define your own triggers, easy to define your own functions, and so on. So Postgres' version of SQL is mostly standard, but they couldn't resist themselves either, and they had to add their own extensions. So once you've built your database in Postgres and made use of all the juicy extensions, you're a bit stuffed if you want to put it on SQL Server or whatever. PostgreSQL stored procedures are quite interesting because in a lot of databases there's a stored procedure language that's defined as part of the database, and potentially there's an SQL standard or close to standard that a lot of databases use, but Postgres does its stores procedures by storing strings. So each procedure isn't stored as some kind of structured thing, it's stored as a string, and what that means is you can define store procedures in a whole lot of different languages. So as long as you've got an interpreter for the language embedded in the Postgres engine, you could define store procedures in Python, Tcl. It even has its own PLSQL-like language, which is in fact very close to Oracle's PLSQL, and that's one place where you could port a Postgres application. It would be quite easy to port to Oracle because of the similarity between Postgres' stored procedure language and Oracle's. But yeah, the flexibility comes from the fact that stored procedures are stored as strings, and as long as you've got an interpreter that can understand those strings and execute them, then you can have pretty much any language as a stored procedure language. Let's see. Well, so there's a quick example and a really silly example of something that could have been done as a view, but I did as a Postgres stored procedure function. So this function returns a set of things. So basically it returns a table composed of tuples of the type bars, where we'd have to define bars. Oh no, we've already, there was another thing in the catalogue. When you define a table, you automatically get a data type which represents the type of all the tuples in that table. So here we're using bars as a data type, the type of tuples in the bars table, and here we're actually using it to refer to the table. Okay. So we've got control structures. we can iterate over this query, and for each result that we get back from that query, we can add it to the set of result tuples. So like I said, this one's a bit silly because you could equally do it with a view, but in any case. Right, so yeah, that's time. It's almost 6 o'clock, so let's stop there and we'll continue on Thursday, 12 o'clock, in a different theatre, Colombo.